Okay, I wanted to welcome everyone here. Should be, sorry. One of the things we're going to ask is that you be tolerant of people having glitches with their technology, even if the glitches are mental glitches. So I'd like to welcome you here. There's 4 of us who have been spending a lot of time organizing this. Myself, I'm at the Woods Hole Oceanographic Institution and was at Nosams for many years. Bob Key from Princeton, who's Mr. Data Man. Roberta Hansman, who's the current staff chemist at Nosams, and Rolfe Sunrup, a data user from University of Washington. And I want to put out a huge shout out to the OCB group, who will be introducing themselves shortly, who have made it, putting this thing together so far, seamless. And I encourage you, if you have any opportunity, if you want to do a workshop or something like this and it falls within the OCB purview, to consider writing them a proposal, because they're very good at what they do. And it's made my job easier. I'm also going to point out that the workshop is planned while working on the ancestral lands of the Wampanoag Nation, made up of Mashpee, Akina, Herring Pond tribes. That's where WHOI is, Massachusetts and Pawtucket, Lumbee and Chesapeake land. We honor and respect the many diverse Indigenous peoples still connected to this land and the lands of our participants. We acknowledge the painful history of genocide and the substantial traditional and local knowledge that Indigenous people hold and sustain. For those of you who are not here, but in other places, please feel free to share the identities of any Indigenous people native to your area in the chat. And now I'm going to hand it over to Heather Benway from OCB to present the OCB Code of Conduct.
Thank you, Anne. Hi, everyone. My name is Heather Benway. I'm the Executive Officer of the Ocean Carbon and Biogeochemistry Project Office. OCB is a global network of scientists working across disciplines to understand the ocean's role in the global carbon cycle and how marine ecosystems function and how they are responding to environmental change. The OCB Project Office is based here at Woods Hole Oceanographic Institution and has received sustained support from NSF and NASA since its inception in 2006. And we do release an annual activity proposal solicitation, usually around August, September. So always keep your eye out for that. And if there are activities that you think OCB can support and bring a good interdisciplinary audience to foster some good dialogue, please do consider it. Spend some time on the website. The OCB office provides support to its network in a lot of different ways, from science planning, activity proposals, and workshop support. We really focus heavily on early career support, providing opportunities for not just travel support, but tuition to take courses in relevant disciplines. Remote sensing is one example. We have been here for a while and we've gotten pretty good at what we do. We have a fantastic team. One of those team members is here today. I just want to give May a quick shout out. May Mahegan, if you would like to introduce yourself, that would be fantastic. May is my partner in crime here.
Sure. My name's May Mahegan. I've been with the project office for 5 years next week, and I do the communication side of it. So I help out the workshops, trainings, that sort of thing. One thing I want to highlight is we do science highlights and science features. So if you have newly published research that's relevant to the community, I'll work with you to do a short write-up, and that goes out to our email list through the newsletter of about 2,800 people and on our website. So I help maintain that information of jobs, new science, support workshops, all those sort of things.
Thanks, May. So yes, OCB is also a central communication hub, as you can gather from having a full-time communications professional in our office. It's a critical part of what we do. And that newsletter and also our Twitter, between those two, we can reach a pretty wide audience. So just a few brief words. Our code of conduct, it's really pretty self-explanatory. The OCB program and the activities that it supports really aim to provide a safe and productive and welcoming environment for all participants, whether in person or on Zoom. We welcome a diversity of views and opinions, and participants are encouraged to respectfully express their viewpoints with consideration of time and space for others to do the same. I don't need to read this. I don't think it's up there and you've had some time to look at it, but definitely if you experience or witness any kind of behavior that's not appropriate, we encourage you to go to our website and report it. There's actually a reporting button on the website, and I'm going to drop this link to this page on our website in the chat here so that you can go there if you need to. Knock on wood, nobody has needed to yet, but I want people to feel like they can, and it is safe to do so. A couple of just brief reminders during the meeting. For a typical Zoom meeting, everyone's video should be off when a speaker is delivering their presentation, except for the speaker, of course. Please mute yourself when you're not speaking. And if you want to ask questions of any of the speakers, you can either use the chat or you can simply unmute yourself, whatever is more comfortable for you. And we will be keeping an eye out in that chat for questions that come in. If anyone has questions about OCB, please feel free to message me separately. I'm happy to talk with you more about the program.
Okay, thank you. And we'll start talking about the workshop. If I can get this to advance. There we go. So the goals of the workshop are pretty simple. We have 3 days. And the first day, we're going to summarize and discuss current methods. We have a lot of presentations, which should be interesting. The second day, we'll talk about interlaboratory comparisons, those that have occurred and those that perhaps should occur in the future. And the third day will be devoted to discussing the development of reference materials for the field. And the final goal of the workshop is to come up with an action plan for the future. The 4 of us organizing this workshop have been talking a lot about this, and we of course have our ideas, but today we're here to listen to the community's ideas and see what we've been missing, and what can hone and improve our ideas as well. The basic day will be presentations at the beginning, a half-an-hour break, and then we'll separate into breakout sessions. We're planning a round table on Wednesday, and we have a number of people from funding agencies, users, data people, but we do not have a junior researcher identified yet. And please consider volunteering. You can volunteer in the chat. You can send me an email, McNichol@whoi.edu. And we'll choose, if more than one person volunteers, we'll just make a decision as to who to include. And if you last to the end of each day, there'll be a raffle to win some OCB swag. So have fun. We're going to start with Kalina Gospodinova is going to talk about the methods in use at Nosams. There's 2 separate methods. I want to point out that Yuishiro Kumamoto was not able to attend this meeting since he's on a cruise collecting C13 and C14 samples. But the method that their lab uses is identical to the first method that Kalina will be, the water stripping method that Kalina will be presenting. So off to Kalina, and please remember mute and video off.
Okay, hi everyone. My name is Kalina Gospodinova. I'm a research associate at Nosams, and I'm going to be talking about the dissolved inorganic carbon extraction methods that we use here at Nosams. So Nosams was originally established to provide radiocarbon measurements of seawater samples collected as part of the Water Ocean Circulation Experiment Program. To better understand ocean circulation. Once the WHOI program was completed, Nosams continued to provide oceanic radiocarbon measurements for the CLIVAR, now GoShip program. And we have analyzed over 15,000, we have performed over 15,000 analyses to date. At present, Nosams analyzes approximately 2,000 seawater and groundwater samples per year, including groundwater samples from the USGS National Water Quality Program and other clients' seawater and groundwater samples. We also routinely run our own internal seawater and groundwater samples that we collect. The following protocol has been used for the WHOI, CLIVAR, GoShip programs and collection. However, we use it for all our sample collection here at Nosams, including our internal standards. And you guys are probably familiar with this, so I'll go over it briefly. So seawater and groundwater samples are collected in clean 500 ml or 100 ml borosilicate glass reagent bottles. They have a ground glass joint and a solid stopper. Prior to collection, all of the components for collection are rinsed with the water we're going to be collecting. So the transfer tubing and the bottles are rinsed first, and then the bottle is overfilled 1.5 times its volume with the water of interest. Then some of that water is removed to allow for headspace and expansion, and the glass ground joint is dried. Then the solid stopper is greased and twisted onto the bottle to secure the bottle. And then the rubber band is, oh, I missed one. We do poison our bottles with 100 microliters of mercury chloride before we put the stopper back on. Once the stopper is on, we secure the sample with a rubber band and gently shake it to mix the poison, make sure the sample is poisoned well. Nosams has two systems for DAC extraction, the water stripping line and the rapid extraction of dissolved inorganic carbon system, or Radix. The water stripping method utilizes a sparging technique to facilitate the extraction of DAC as CO2 from an acidified sample and into the headspace. And this system has been extensively used to process water samples at Nosams from the inception of the facility until very recently. In April of this year, we approved our second DAC extraction method to analyze GoShip and client samples. And the Radix system uses a gas permeable polymer membrane contactor to extract the DAC CO2 from an acidified water sample directly from the water phase. And I'm going to go a little into details of both of these systems. So this is a schematic of the water stripping line. The water stripping line is fully automated and has the capability of analyzing 10 samples at a time. Until recently, we had 2 of those systems in the lab, but we retired one of them, and we're actually building a second Radix system. When we're ready to analyze our samples on the water stripping line, we analyze them in the bottles they are collected in. Each sample is first put into a nitrogen glove bag. The solid stopper is removed and it's replaced with a stripping probe that has 3 ports. And I actually have one of those here to show you guys. Oh, maybe I can't show you. I don't know if you can see it. So I think I'm gonna do this so you can see it. So this is the probe. It has 3 ports. 2 of those ports have valves, and one of them has a septum, which allows for the acid to go in. And one of the ports is extended into the bottle and ends in a fret. So that is what the probe looks like. So once the samples are ready and have their stripping probes attached,
Kalina,
Yeah,
can you X out of the background filter view?
I think I did.
It still shows up on the presentation.
Does it? Oh, I selected that. Let's see.
So top right of that box.
So maybe I need to close it.
Perfect.
Can you see? Oh,
Yep.
okay. So I
Thank
changed it, but never closed it. Okay, so
Yep.
I'll show you this
Thank you.
again.
We could see that. That was great. It was just the slide that was obscured.
Okay,
Thank you.
great. Thank you. So yeah, when we're ready to attach the samples to the line, we attach them through the 2 ports that have the valves, and then all the lines of the are evacuated, and then the recirculating loops are filled with extra pure nitrogen gas. So let's see, these are the recirculating loops. And once they're filled, we acidify the sample with 85% phosphoric acid, and we turn on a recirculating pump that recirculates the carrier gas and the which goes through the treated part of the probe, extracting the CO2 out of the sample into the head space, and then the carrier gas with the extracted CO2 is circulated through a water trap and liquid nitrogen CO2 traps where the CO2 is frozen out of the carrier gas. And the recirculation lasts for about 10 minutes, at which point the extraction is complete. The carrier gas is pumped away. The liquid nitrogen traps are warmed up, and the extracted CO2 is transferred to a quantification region where it's manometrically quantified. And after that, it's transferred to a glass manifold and stored for further stable radiocarbon analysis. So this is our water stripping line. Okay, so this is a schematic of the Radix line. Similarly to the water stripping line, the samples are analyzed in the bottles are collected. However, Radix has a different kind of top, which I have here, which is also placed on the sample in the nitrogen glove bag. The sample is sucked out of the bottle through this peak line, and it's displaced. Actually, we're displacing it now with nitrogen through a check valve. So similarly to the water stripping line, Radix is automated and it can analyze 10 samples at a time. Part of the samples, about 50 mils, are used to rinse a sample loop, which is indicated in blue here, and fill a sample reservoir. And after the 50 mils, we fill the sample loop with the sample we want to with the water we want to analyze. Once the loop is filled, we recirculate that water into that loop. Simultaneously, a small phosphoric acid loop is filled with a phosphoric acid, 85% phosphoric acid, and the membrane loop is filled with the gas milky water, and the membrane loop contains the membrane. So once all these 3 loops are loaded, they're combined into one loop and recirculated through the membrane, allowing for the acid sample and the gas water to mix. And the extraction starts. While the acidified sample is circulated through the membrane. A helium gas stream is stripping the extracted CO2 and passing it through a water trap, and again, a liquid nitrogen trap where the CO2 is frozen down. Just like the water stripping line, after the extraction, the CO2 is transferred to a quantification region on the line, quantified, and transferred to a glass manifold for further analysis. So as I mentioned, we have a groundwater internal standard that we run routinely with our samples. It's a sample that's actually radiocarbon dead, and we collect in Fort Caswell in North Carolina. This is data for the latest collection that happened this year at the beginning of the year, and we started running it about April of this year. And you can see this is the water shipping line and Radix data, C13 data, and where you can see that Radix is a little more precise at this point, where it's sort of like a running precision number that we keep track of. And this is the fraction modern of the same data set, and you can see that both lines are equally precise and are in great agreement. So here I also have some data that there was an intercomparison study of DIC13 published by Chenkino in 2019. Unfortunately, Nosams was not a part of it, but we were able to obtain 2 bottles of the certified reference material for oceanic CO2 measurements, batch 157, which came from University of California, San Diego Scripps. And we were able to we took those 2 bottles and we split them and ran them in multiples on both the water stripping line and the Radix line. And you can see that they're sort of in agreement with the variability we see of the accuracy across the 16 labs that were part of that study globally. So it's a great experiment. It will be wonderful to have more sort of reference material that we can all run and kind of explore how our methods differ globally. So that's what I have. If you guys have any questions, please let me know. I will be here the whole day.
So people can unmute themselves or ask a quick question, because Kalina's presenting 2 methods, she gets a little more time than everybody else. So if anybody has a question, have at it. So. But
Kalina, I have a question. Paul Middlestead here.
Hi, Paul.
Hi, guys. I was wondering, what is the lowest concentration that you can achieve with either methods?
Oh, so the water stripping line is somewhat more versatile at the moment, because we would, you know, you can run a larger volume. So low concentration samples, which happen with our USGS analysis, would go on the water stripping line. The second Radix we're building, we're hoping to put in more capability for various concentrations. So the sample storage, that's part of the sample loop. We would have different size sample storages that can be selected automatically, so you can analyze a different amount of water.
Right, but your lowest concentration that you can achieve with confidence is what, 1 ppm?
So that's limited by our, you know, MS machines, really. So you can, we go down, and I don't know, Roberto can also comment on that. We usually go down to micromoles.
Okay.
So if you can extract that.
so also,
Sorry, Anne.
I was just going to say, what in the Radix system, one thing that limits it is the sample volume thing, and that can be designed to be virtually any size. So at present, it's approximately 50 mils. Is that correct?
That's correct. So we're, we don't do a very low DIC samples on it. But you can really design at any size you want it to be. It's just increasing the reservoir space of that loop that limits it.
Okay, thanks.
Okay, there perhaps one more question, or we'll just move on to the next speaker. All right. I'm assuming José Quintanilla is in the room and can share his.
Yes, I'm here. Hi.
Okay. So. Oh, and thank you, Kalina. Sorry.
Jose, so the screen share is the bottom of your screen. You look for a green button.
Yeah, I'm
in the
looking.
window.
I don't know what's happening. Well, first of all, I want to thank you all, and Roberta, Robert, Rolfe, and everyone involved for inviting us and giving us the opportunity to learn from all of you. I think it's a great way to share what we all are doing. So then let's click here. All right. So
I also forgot to thank the people who are not on East Coast time for getting up at strange hours to give presentations.
it's 7 a.m. here, so I'm just waking up. So sorry for. Are you seeing something? No.
No, just you. If you're not able to do it, May can bring up the stuff that you deposited, and then you can just tell her when to advance the slide. So.
Yes, please. If you could do that.
Okay. Yep. Just a sec. I'll bring them up.
Thank you very much. Excellent. All right. So, well, I'm José Quintanilla, and I'm a student in CICESE in Ensenada, Mexico. I'm working with Juan Carlos Cerguera in his stable isotope laboratory. And there we have two wonderful technicians, Axel and Doreni, who really do all the heavy lifting for us. And we are three students that are working there. Can you go to the next slide, please? So, yep. So this is the laboratory, and this is the instrumentation we use. We have two thermofinnegan Delta Plus mass spectrometers. One of them is cooped to an elemental analyzer, where we do organic samples, and the other one is cooped to a gas bench, where we do all the inorganics and the dissolved inorganic carbon. Today I'm going to focus on the technique we used for the gas bench, as I believe is the one in more dire need of revisitation. It's an old technique, and that has some pros and cons, as I will tell you. Can you go to the next step, please? Thank you. So, well, as all of you know, the first step in all of these methods is to collect the sample. We collect them in 100 milliliter glass bottles using the standard technique of rinsing and flushing to the top and then filling it again. We preserve the samples with mercury chloride. and then we seal them with a crimper. So here is the first, let's say, like problem of this technique is we use these 100 milliliter glass bottles that are really big, and they occupy a lot of space for storage. The pros obviously is that we have seen that this kind of bottles really preserve the sample. There's no entrance of gases, and with the mercury chloride, there's no biology, as we have seen. We have tried other methods for preserving the sample, but this one is the more stable for us. Can you go to the next one, please? So quickly, this is the storage. Usually after every cruise, we have like 5 to 6 to 7 boxes like this with 700 samples that we take. This is from the Gulf of Mexico, and then we take this to the lab in Ensenada. Can you go to the next, please? Thank you. And well, the technique, once in the lab, what we do is we flush 12 milliliters hexateners with extra pure helium, and then we transfer the water sample from the 100 milliliter bottles to these hexateners. We just use 0.5 milliliters to the clean hexateners, and as I told you, the problem is we stay with a lot of water that we don't use, and then the hexateners we acidify them with phosphoric acid, and then we leave them to 12 hours of reaction at 16 degrees Celsius. So as the carbon dioxide goes to full equilibrium, and then we measure them with the mass spectrometer. Can you go to the next one, please? So mainly the focus here of the presentation would be the standards, the reference materials. In this lab, we use some carbonates, which will be the NBS 19, the LSBEC. Here I show you the values, the international values, 1.995 per mil and minus 46.5. The NBS has a reference, a value that's close to the waters, to the DIC of the water, but the LSBEC, as you can see, is really low. So, but it works. It's really stable also. Both of them, we have an internal precision that we have been measuring for 10 years of less than 0.02 per mil. And we also use many internal reference materials as a carbonate, a mercarbonate, and some green dead calcite that we rented, and we have been using the same one for quite a while. They are a little bit less stable, and we have less precision with them, but they also work. And then obviously, well, the problem when working with waters is you need a reference material that's as close as possible to your samples. So we also use many water standards. Can you go to the next one, please? Thank you. So we use this batch 98, the standard that we have that's usually used for DIC measurements, but we have seen that for delta C13, it's also somewhat stable, and it has a value of 1.41. That's close to our waters. We use also a bicarbonate, a sodium bicarbonate solution that we made, which the value is low, but it's also somewhat stable. And we use water from the depth of the Gulf of Mexico, whose values we have seen is the more stable and more constant, let's say. So we use this water from 2,000 meters and 3,000 meters, sorry. So these standards help a lot for the corrections. And although all of them are internal, we are aware we would need more international standards, water standards if there are. But for the time being, they serve us, and they are pretty stable, and we think we have a high precision with the method. Can you go to the next one, please? So a daily run will look something like this. We put our 30 standards and 30 samples. We left them here in the auto sampler to digest, for the reaction to occur during 12 hours at 16 degrees. And then the auto sampler takes each sample. It takes like 10 minutes per sample to run in the mass spectrometer. As a continuous flow spectrometer, we make 10 aliquots of each sample, which allows us also to leave all the extremes and bad measurements. This gives us also a more precision and allow us to see how the evolution, let's say, of the standards with time. So here, well, there was this equipment has also the way to put the acid to be automated, the phosphoric acid, the injection, but we have seen that it's really messy for us. It always leaves some acid in the septums of the excitaners, and that acid goes to the chromatography column, which of course it's not good for anyone, unless for technicians who have to clean it up. So we put the acid manually, and that obviously all of that takes time. It's like 5 hours of preparation, and then the 12 hours of reaction. Can you go to the next one? Thank you. So here, just to present some results that we have been sampling the Gulf of Mexico for over 10 years now, in many cruises. So here I present you like 2,900 samples, more than 4,000 replicates with an internal precision of 0.047 per mil. And just to show here what we have been seeing, this Suez effect, the delta C13 minimum that's been getting shallower with each year passing, and we have been able to measure that with somehow some precision with this method. So in the right graphic, each color, well, it represents the average of each campaign, and as you can see, the purple one is in 2010, and then the red one is in 2019, and we have seen this effect. Then can you go to the next one? And so, just to summarize this method and what we believe are the pros and cons of this analysis. Well, the pros, we believe we have a high precision, relatively high, below 0.05 per mil. The collection and preservation of the water samples is relatively easy to make. And as we use just a low volume of water, just 0.5 milliliters, we can make as many replicates as needed. That's a good thing. And also we don't use much standards. Let's say we just weight 100 micrograms of NBS 19, all those reference materials, so they last a long time. The cons obviously is the high volume of storage. Also, we're producing a high volume of residues with mercury, which obviously are treated, but well, it's something that we would like to minimize. We use too many standards, although the quantity of each of them is low. We used a lot, and also it's a slow technique, as we only measure 30 samples per day. We could measure a little bit more, but 30 samples per day is like the quantity that we are comfortable with. And well, that's it. And thank you all.
All right, thank you very much.
Thank you.
That's a beautiful record from the Gulf of Mexico. I'm very impressed.
Yeah,
We
nice.
don't really have time for questions, but unless if there's one question, we could perhaps, but keep up the good work.
Thank you. Thanks a lot.
And people can ask their questions in the chat or in the breakout rooms. So the next speakers are Brett and Jennifer Walker, who will talk about one of the two sets of methods in place at Ottawa. It's all yours.
All right, thank you guys. Thanks for I see that this actually, let me stop sharing my screen 1 second. Got a screen mirroring problem. Thank you for your patience. Okay, can you see my slides?
Yes.
Okay, thank you. Thank you so much for having us to speak today. Today, I'm going to be presenting a method that really was established at UC Irvine and we've been using for many years and have recently gotten in place in my lab at Ottawa. So this is a lot of collaborative work that we've done over the years with Xiaomei Zhu, Dashun Zhang, Sheila Griffin, and Ellen Druffel. So it's a twofold method, and Jose did a wonderful job introducing the gas bench method technique, so I'll try and skip over that. Okay. All right, sample collection. We collect into 250 ml media bottles with the GL45 caps. These are the same bottles that Andrew Dixon uses at Scripps for total CO2, and we've found that they actually preserve DIC samples very well it can be stored for several years before analysis. We don't typically filter, so we use a silicone tubing to flush the vial. As you've seen before, we do 3 times overfill, collect with 0 headspace, and then cap. So in this way, since we don't filter, this is really TIC, but we're assuming that PIC concentrations are sufficiently low not to skew our measurements. After collection, we take them back to a wet lab on the ship and open them quickly and add 1 drop of saturated mercuric. That's what we found to be the best way of preserving samples. Then we cap them and let them warm up and tighten them up 1 more time before just storing them at room temperature in the dark until they're ready for extraction. Just to go over our 2 methods of sample preparation, they're fairly similar. So we take these bottles into a glove bag. Typically we use helium and prepare 14C and 13C at the same time. For 14C, we use 60 ml iChem bottles or vials, and we just decant into these 60 ml vials in the glove bag. And then we use a Hamilton gas tight syringe to add some 85% phosphoric acid. And then we react these samples just to speed up the acidification on a heat block at 75C for 2 hours, and then extract on a vacuum line. For 13C, we, instead of decanting, we pipette typically 1 milliliter of seawater into gas bench excitainer vials and acidify with the same syringe Jose showed you, with, again, 85% phosphoric. You can use nitrogen for preparing 14C samples, and we've done that successfully at UOttawa. But for 13C, obviously, it has to be helium. For our standards, we start out by preparing some CO2-free water, and typically we'll just acidify either millicue water if we're preparing a freshwater sample set, or seawater that we've collected, like waste seawater. So we acidify that inside a glove bag and sparge with helium for 15 minutes and cap it, and then we find that it's pretty good to prepare samples, or sorry, standards. For 14C, we typically weigh powders into small glass cuvées at the desired mass. Typically, we size match all of our standards to our sample sizes. And then we'll open these more IChem vials, and we'll add the cuvée to the IChem vial, and then we'll add 45 ml of stripped water. For our technique, I forgot to mention on a previous slide that the volume you add to this IChem vial is very important. Maintaining a constant pressure is also important inside these vials, especially for 13C. And so with this volume is determined to maximize the efficiency of the headspace CO2 you'll generate. And so for 45 ml, you're gonna get the maximum yield from seawater. So after doing that, add the water to the standard and cap it inside the glove bag. The standards we typically use for 14C are IAEA C2, which is almost half modern. We use radiocarbon dead bicarbonate, which is easy to come by. And then we use a coral standard that Sheila and Ellen developed at UCI that is more modern. Over 10% of our analyses are always standards, so we run a lot of standards. For 13C, it's really a lot like what was shown previously. So we'll again add, we'll weigh powders into excitainer vials, but then we can just purge them inside the glove bag and add however much volume your samples are, we'll add the same amount of stripped water. And then one key difference for us, we found that it's really important to then remove the same volume of water you added to that standard in helium. So to maintain a constant pressure inside the, we try to stay at atmospheric pressure inside the vial. So typically we use S19, we have an OXG standard from Oxford. We have our own CA14 as an internal standard that we've calibrated at UCI at a few labs, and a CalX standard. We also use a bunch of calibrated monitoring gases on the gas bench that we can flush excitainer vials with to parameterize our glove bag blank to make sure we don't have any entrainment of air across the sample set. After samples are prepared, so for 14C, again, I mentioned we react these on a block at 75C. This is to speed them up. You can do multiple sets per day this way. And then after CO2 is evolved in the headspace, we extract it with a gas-tight syringe. And then we inject it directly through a Septiport on what you would think of as a classic cryogenic vacuum line. So the CO2 then is purified through a slush trap and liquid nitrogen, and then quantified manometrically. And if you so choose, you could take splits at this time for 13C, if this wasn't DIC. So this is, for other sample types, we would take splits for 13C this way, but for DIC, we found that this headspace method when you react and extract for radiocarbon this way, it can fractionate 13C. So that's why we do this separately on the gas bench. These samples are converted to graphite, and we can do about 20 samples per day. Typical sample masses for seawater are about 0.5 milligram of carbon, and those are run by AMS. For gas bench, we do the same method as Jose showed. We equilibrate for 12 hours at room temperature. We typically prepare 50 samples at a time, and then the rest of the gas bench block is standards, and these are run over the course of about 3 days. Just wanted to show you, we just have a couple of data slides. This is some of the data we generated just this past year in our lab. So we've been running this method for a while at UC Irvine, but we just got our line set up at Ottawa, and we're able to run about 100 samples through the line. So this is just showing on the left some of our dead carbon standards, so the bicarbonates. And this is a plot of ratio to OX1 versus sample size. So these are all fairly big size standards, ranging between 300 or 400 micrograms to almost a milligram. Through this plot, you can determine roughly how much modern carbon blank this process adds. And for us, it's about 2 micrograms of carbon, or less than 0.5% of the sample is modern carbon. We typically achieve backgrounds of about 46 to 47,000 years. So that would be a D14C value of -997. And we use those backgrounds to, again, subtract off of our measured samples and correct our modern standards. So just the standards we've run in the past year, we use, again, 2 of these standards I mentioned before, the UCI Coral standard, which is modern, and IAEA C2, which is about half modern. And these were parameterized using a direct acidification method. So we're using them as DIC, but these were parameterized with direct acidification. Based off what we've done over the past year, we've found that our corrected standards match pretty well to these consensus values. So on average, we're about 0.5 per mil high over these 2 standards, our corrected data. We've run about a little over 100 unknowns. This is all from a Baffin Bay cruise we did in 2019. So our blank corrected precision for unknowns is about 1.5 per mil. That's propagated measurement precision. The average of our true sample duplicates, where we take 2 separate DIC bottles and extract them on separate days in the glove bag and run them on separate wheels, is about 1.2 per mil. That we had about 10 of those in this sample set. But that offset can range, right? So sometimes they're bang on, they're 0.1 per mil off, and then sometimes they're about 2 per mil off. And that's actually fairly, that high number, the 2.2 is pretty consistent with our overall variance on these measured standards that we did, which is about 2.2 per mil overall. For 13C, I just thought I'd show you this is actually data generated at UCI, but it's longer term data. So we have on the left about 3 to 4 years of data from our standard runs. And you can see the total reported error of this long-term average is about 0.1 per mil. Again, for 13C, 10% of our samples are always run in duplicate. And for 95% of our bottle replicates, we find standard deviations less than 0.06 per mil. So they typically are really, really tight. Very occasionally, we'll have higher uncertainties where one replicate might be 0.15 per mil different from its duplicate. On the right, we've had I'm showing just a couple data sets. We've had the chance to do a couple intercomparisons for 13C with about 4 different labs using this technique. The left plot shows freshwater comparison between our lab and a contract lab. And in this intercomparison, the data match pretty closely. And I think it's fairly reasonable what you'd hope to see when you're doing intercomparison work. But one time we did an intercomparison with a contract lab, and we found significant offsets. And this is on the right, I'm showing seawater, Del 13C, depth profiles. And we found a fairly significant offset in the 13C profile. The profiles mirror each other, suggesting that they were both analyzed correctly, but what we have is a calibration standard issue. And I think this really harks towards what we're doing here today and demonstrates the need for interlaboratory comparison standards. We can generate DIC concentrations using this method. It's not as precise as like the ghost ship methods, but it does seem to work reasonably well. Okay, and I just wanted to end with a couple of important considerations for generating high precision 13C data. And you can contact Jen for more details on this, but in essence, there are significant effects of volume, sample volume, and pressure inside the excitainer vials on the type of precision you can generate. So when you're adding less, what we found is that when we add less than 2 ml of sample, we get more precise data. And when we add more than 2 ml, we get less precise data, and we see a big decrease in signal to mass ratio. And
Brett,
that's,
can you wrap it up in a half a minute or something?
Yep, this is my last slide. So just to say that equalizing that pressure is very important. Based on the excitainer data, we found that the samples can remain in the excitainer vials for about a month before analysis, just fine. If the septa's pierced, you'd like to run it quicker, maybe in a couple weeks. And we've done some work just showing that with exposure to air, you can have rapid equilibration in freshwater and seawater. And just in 5 minutes, you can start to see offsets, measurable offsets on the gas bench. And we've determined that that is mostly due to degassing. So it's some carbon loss actually in the sample. Okay, that's all I have. And thank you for your time.
Thank you. I don't think there are time for questions, but thank you. It was a nice presentation on a different method. And people can ask questions in the chat, which have been done, and hopefully if there'll be time at the end to just have some general questions to different speakers. The next speaker is also from Ottawa, Sarah Murseli. I hope I'm pronouncing your name correctly. So the floor is yours.
Thank you. I'll share my screen. Everyone see that okay?
Yes.
Okay, great. So I just wanted to thank the organizers for putting this workshop together and the opportunity to participate. This is really great for our team. I'm Sarah Murseli. I'm the radiocarbon unit manager at the radiocarbon lab, AEL-AMS. We're a contract lab. We process about 3,000 to 4,000 samples a year, different material types, including DIC and water. Of that, we probably about 200 to 300 samples a year. Our method is largely used for freshwater, but we can process saline DIC for 14C. So our method, we use these these bottles for sampling and extraction. They're Wheaton bottles with a special closure, 33-430 size, with a butyl septa and flange. So we put them through a careful cleaning process, which I've summarized here. What's nice is the bottle sizes range in volume from 125 up to 1 liter, 125 mils up to 1 liter. So you can target the volume that you want to sample. And ultimately, we ask the user to send us enough sample to yield 1 milligram of carbon. We recommend to filter in the field with pre-baked glass fiber filters, 0.45, but these are really hard to find. And it really depends on who you talk to, hydrogeologists, oceanographers, biologists, on what their operational definition of DIC actually is. Some work with the 0.45, some work with the 0.7. So we usually go by the client's definition. So yeah, we asked the user to submit enough sample to yield 1 milligram of carbon. Forgot to mention during sampling we recommend to add a drop of saturated mercuric chloride to poison and preserve the sample. So ppm DIC concentrations are known at the time of submission, and we target the volume for CO2 extraction to yield 1 milligram of carbon. We transfer the sample to helium flushed bottles in a glove bag, leaving about a half head space in the bottle. Samples are acidified with 85% phosphoric acid to minimum pH 2 or less and heated on a hot plate for 1 hour. So here's a picture of the sample bottles heating with a dummy bottle thermometer to monitor the temperature. So here's a schematic diagram of our extraction line at AEL. It's a 2-stage flow-through system which uses a high purity helium carrier gas to sparge the DIC from the headspace of the bottle. And this is coupled to a vacuum extraction line. So the helium carrier flows through at a rate of about 200 mils a minute. The sparging needle is inserted into the acidified sample, and the exit needle sits in the headspace, and we flush the volume 10 times. And that helium carries the CO2 sample to a stainless steel U-trap packed with quartz silver wool at liquid nitrogen temperatures and traps the CO2. And then the helium carrier is purged to atmosphere on a pigtail. And then pictured right here is the extraction bottle showing the entry needle in green and the exit needle out. And here's just an actual picture of the extraction line, a little messier, but showing the helium coming in. Portion it splits off to the Nafion gas dryer, and for counterflow to help with drying of water, or H2O removal, and that's regulated at about 2 times the flow of the carrier gas. This also tees into our methane line on the left, which is not pictured, and then the vacuum line on the right. So for CO2 extraction, we allow the whole line to pre-flush for 5 minutes between samples. The sparging needle enters first, followed by the exit needle. And as I mentioned, the volume is flushed 10 times. Following sparging, the CO2 is transferred to a vacuum line for cryogenic purification and CO2 quantification, and then sealed in a brake seal. And we pre-pack these brake seals with silver cobaltus. And once sealed, we bake at 200 degrees for 12 hours to mitigate any sulfur impurities or halogens that might interfere with graphitization. So for standards, similar to those that Brett outlined, we use sodium bicarbonate as our dead standard and IEA C2 as our known age. We are searching for a modern reference. We have a coral standard, but limited quantities. So that's one reason why we're here today. So the solid standards are placed in extraction bottles and heated to off gas any absorbed CO2. And then acidified water is added to the bottles and then heated. So samples are graphitized using in-house made hydrogen reduction lines. The samples are pressed and carbon isotopes are measured on our 3MV HBE-AMS. We're happy to report we had a McCaddis installed in September, so we're excited to start playing with that. So here's some background results from our process blanks. So our typical background is about 42,000. we're hoping to improve this a little bit. Modern carbon blank estimated at about 3 to 5 micrograms of carbon. And for our known reference, IEA C2, we're pretty close to consensus value. Our typical reported precision on a measurement is 4 to 5 per mil. So just acknowledging some of our team here with our newly installed Macatus, and those that work specifically on the DIC measurements, Shelley, Zhao, Jennifer Walker, and Carolina Krim. And that's all. Thanks.
Thank you. We have time for questions, so you can either unmute yourself or put them in the chat. But since this is a workshop, speaking and identifying yourself is a good thing as well. So I had a question. You said you also, you're focused on groundwater, but you also do seawater. Do you find that there's excessive bubbling when you use seawater, which was
when we acidify and extract the sample?
Yeah.
I haven't noted that. Sometimes we notice strange colors for hypersaline groundwaters. I think that's just metals and other impurities that are reacting. But no, I haven't noticed. Maybe Carolina can comment. She's worked with hundreds of these samples, but not that I can recall.
Yeah, I also haven't really noticed any crazy bubbling, but we also don't get saline as often. I feel like most of our submissions are freshwater.
Okay. We used a fritted piece of glass, and I think that caused the bubbling more than what you have been doing. Are there more questions, or shall we catch up on some of the time we're sliding on? All right. So the next speaker is Katy Sparrow, and you can say, but thank you, Sarah. It's all yours, Katy.
Okay, thank you. Okay. All right. So just gonna minimize that. Okay, so I'm just going to be presenting the radiocarbon and C13 methods at Florida State in Jeff Chanton's lab. I was a postdoc with Jeff from 2018 until this summer, and I'm now at Georgia State University. Okay, okay. So instrumentation in the Chanton lab, there is a gas chromatograph coupled IRMS for both C13 of DIC and C13 of methane. We also have 2 custom vacuum lines for preparing discrete vial samples to purified CO2, which is sent to Nosams for graphitization and for AMS measurements. I'm going to be talking a little bit about all 4 of these methods, not exhaustive at all. And unlike some other presenters today, I don't have the exhaustive records of precision and accuracy for the instruments, but I do have quality control that I directly measured in some cases. So less exhaustive. For sampling and preservation first, again, sampling from Niskins into 60 milliliter syringes, and then 20 milliliter aliquots from each syringe are transferred to pre-weighted, evacuated 30 milliliter serum vials, which are crimp capped with butyl rubber stoppers. The pre-weighting is obviously for the concentration measurements, which are also carried out on the IRMS in our lab. rather than the isotopes. Each vial is poisoned and acidified with 1 milliliter of 20% weight for weight nitrogen bubbled phosphoric acid solution. Vials are stored stopper side down, and once in the home lab, the vial headspace is filled with helium via an open split, yielding atmospheric pressure in the vial. The isotope standards, we also use the NBS 19 for a C13 standard. Again, it's as mentioned by Jose, I believe it's great because it is close to the DIC signature in the ocean, plus 1.95. We place a weighted amount, usually just a grain or two, very small amount, in a 30 milliliter serum vial, stopper and crimp cap it, fill to atmospheric pressure with helium, and then acidify it, and then inject it into the IRMS for a C13 DIC measurement. We also have an internal standard, which is a mineral sample from Jeff's rock collection, a sample of crystallized calcite, spar calcite. It is radiocarbon dead in the interior layer, which we reach by shaving off the edge of the sample, discarding this edge layer exterior, which is more collaborated with the atmosphere, and collect the interior shavings then from an edge and place a weighted amount in to a vial, about 5 milligrams. Stopper the vial, crimp cap it, fill to atmospheric pressure with helium, and then acidify it. And we do one of two things with that standard. We either use it as an internal standard with the IRMS, or we use it as a fossil known age standard for the radiocarbon DIC vacuum line. So some results from the IRMS for validating the C13 measurements, and this is these are both for some studies that I was directly involved with. So just a few values here. But for the NBS 19, for 3 runs, an average so that was for 1 vial, had a value of 1.87, which is just 0.08 per mil different from the true value. For spar calcite, again, that's there's not a known isotope value for that mineral sample, but 3-run average was negative 10.58. And this was just 0.41 per mil difference than run at Nosams. And this is after preparation on our vacuum line. So that was just an aliquot. So it was, we sent that sample for radiocarbon measurement, and we also had C13 measured on one of those aliquots from the CO2 that we had prepared. I'll show you that. I think it's an average of about 6 samples there, that negative 10.99 per mil value. It's on the next slide. And some C13 measurements of methane. This was measured by Cedric Megan. And his method for actually preserving methane after sampling was using addition of a base solution. He has a limnology and oceanography methods paper about that. And it's with the addition of either potassium hydroxide or sodium hydroxide, actually. But this profile showed from 2 different sites in the Gulf of Mexico, different C13 signatures at those 2 sites in the surface waters. And both of those, these were all measured at FSU on the IRMS. Okay, so C14 DIC vacuum line. General overview is, so it's just one sample being prepared at a time, unlike Nosams 10 at a time. So fairly low tech, but it works for very well. And so we have a sample vial, and it is being, there's a long needle and then a shorter needle leading to the secondary vial. And the secondary vial, same thing, a longer needle extending to the base, headspace is sampled at the top. This helps exclude water from going any further into the line. We also have a dry right trap on the outflow from that secondary vial. Helium is used as the carrier gas here for this line. And there are 4 traps, cryogenic traps, one for the helium purification before it goes into the sample vial, one for concentrating the CO2. There's a water trap prior to the quantification in the calibrated volumes, and a pump trap. Some results. This is from studies of the northern Gulf of Mexico. Have a profile here on the right showing samples both in 2011 and 2012 compared to 2018. We're seeing somewhat of a more depleted signature in those in the 2018 profile. So we studied it fairly high resolution in that surface water to help capture that signature. And here we have our spar calcite. Again, that's our radiocarbon dead mineral sample, internal standard. And at the beginning of this sample preparation period, this was for the 2018 samples, had ages that were closer to 27,000 years, but we had several that were approaching or reached 50,000 years of age. And here's the C13 results that we then compared to our IRMS measurements. So then we have our radiocarbon methane vacuum line. I'll just spend a minute on it since I know it's not the focus of this workshop. We recently moved both of these lines, the DIC and the methane line, to a new lab while I was a postdoc with Jeff. So it was a big re-putting together process. Our department moved to a new building. So I recently put these together and both were leak tight. No modifications were made. I just really focused on putting them back together the way that they had been. And some validations for this line that I performed. We used just a methane gas standard, which is derived from natural gas, so it's fossil. And for a 2-week sampling period, sample preparation period, had these blanks. Here was at the beginning after about 1.5 years of not being used. The blank was not as good. It was around 27,000, but then quickly achieved very good blanks, methane blanks. And we also did duplicates for these anonymized samples here, which yielded very close agreement both at the beginning and the end of the sample preparation period, good agreement with values. And then I also prepared different sample sizes. So I was actually preparing vials in series because the samples were relatively low concentration for this permafrost thaw bog that we were preparing samples for. And when I prepared 2 different, either 2 vials or 4 125 milliliter vials of the sample, I got good agreement with C13 and with C14 signature. And that is all I have for today.
Okay, thank you. We have time for one question. It's interesting, you know, you're talking about the background going up for lack of use, thinking about the pandemic and all the lines in so many studies that have not been used for so long.
Yes, yes. We usually get a good total carbon blank and then begin a standard, but even then, the blank isn't as good at the very beginning.
Can I ask a quick question?
Yes, please do.
You mentioned that you put once you acidify, you put the vial upside down with the septum to the bottom. Did you make a comparison? If you put upward, it will leak gas or what?
Not that I know of. I don't think that we have done that comparison. I love all of Brett Walker's amazing comparisons with doing an action and not doing an action. But I believe we just turned it upside down just to prevent any exchange, any possible exchange through the stopper.
Okay, thank you.
All right, well, thank you. And I'm going to give this over to Rolfe, I think, who he can explain what is going on with he and a consortium will be presenting UW's methods. You're muted.
Good morning. There's the sunrise. Check it out. It's just halfway down my face. We have a video from Terry Rolfe, who is the lead analyst at the UW Stable Isotope Lab. Terry also submitted a set of 5 slides that I can talk through, although I noticed that Paul Quay and Jonah Dirks are in the audience out there, and they may be a little more qualified to do so. So I think we should start off with the video that Terry submitted. The focus at UW has been on the Del C13 of dissolved inorganic carbon, although I should note that during WHOS, during the 90s, we submitted aliquots of the gas to Nosams for C14 analyses. Let's see. Here we go. Check it out. I didn't even do anything.
Hello, my name is Terry Rolfe. I am the lab manager here for the Stable Isotope Lab at the University of Washington's Oceanography Department. I'm very sorry that I could not be there in person today to do this presentation. However, hopefully this video will do a nice job of informing everyone on how we perform our DIC Del13C analysis. So here, our analysis can be broken into 2 main steps. There's the DIC extraction and then the Del13C analysis step. As far as the extraction goes, that is performed on a vacuum line, such as the one behind me. We begin that by taking a stripper, 1 milliliter of 50% phosphoric acid to it. We'll evacuate it, weigh the stripper, add roughly 100 milliliters of seawater to it, and then weigh it again so that we know exactly how much seawater we added to the stripper. Place it back on the line and begin the stripping process by flowing helium at roughly 80 milliliters per minute through the helium or through the stripper, and then we'll trap the DIC down the line. To get an idea or measure the DIC yield that we have collected, we then expand that trapped CO2 into a volume that we have well known, and then measure the temperature and the pressure to calculate what that DIC yield is. The last step is then freezing the DIC into a sample bottle, like the one here, which is then what we use to transport the DIC to the mass spec and do the mass spec measurement. So the last thing that we can do on the line is by running a blank. What we do is we just reprocess that same DIC water that we just ran a second time, and that will tell us whether or not we are fully extracting all of the DIC or if we're missing something on the line. So it ensures it's a nice quality check for us there. We use working water standards to measure the DIC yield and track the del13C. The DIC yield is a quality control check for us. And it's a nice way to verify that there hasn't been any fractionation that has been introduced to the sample or standards prior to their measurement on the mass spec itself. So we use a few different water standards here. In-house, there's freshwater seawater standards that we collect and make fairly regularly. And then we've also been trying to use an instant ocean salt mix for working water standard. And it's actually been turning out pretty good consistent results. So it's possibly a way to go forward for us as well, rather than just only having the fresh seawater type of standard made in-house for us. All of our DIC yield extractions are calibrated by using Andrew Dixon water standards. That way we know that the DIC yield numbers we're getting are representative and realistic and accurate. The final step is that mass spec measurement, and that is for us is performed on a MAC 253 multi-port dual inlet method. The DIC samples are measured against our working reference gas, which is calibrated against PDB by measuring against a NIST standard. So our working gas standards are kept in bottles such as this one here. We'll have several of these made at any given time, and those are all used to track how one bottle is changing over time, or multiple bottles may be changing over time, potentially due to use. It'd be nice to measure against NIST more often, but that they don't supply that a lot of it, and you can only get it every few years. So that's why we keep several of these created and used to track changes just in the use. All right, I think that's everything. So hopefully, if there aren't any questions, all right, I will hopefully see everybody later. Thank you.
Okay, so Jonah Dirks, also from the UW Stable Isotope Lab, has been volunteered to go through a set of slides that Terry Rolfe has submitted. May, I have a question for you. Should I share my screen and have Jonah go through that, or do you want to share those slides?
Yeah, I can share those, Jonah, unless you've got them yourself.
I've got them, so I can just share them so that you know, I can change through them as needed.
Perfect, thank you.
All right. So this is basically just going to be a brief overview of pretty much everything Dr. Terry Rolfe just walked you through, but here is a better picture of our line, and you can see here's where that stripper is, and it goes through a series of water traps. These are a dry ice slush, and then here's where we condense down our DIC in these two, excuse me, liquid nitrogen traps. The seawater DIC is extracted through acidifying, as Terry mentioned. That's a 50% phosphoric acid mix, stripped out and trapped in a vacuum flask. The DIC concentration is estimated from an anometric CO2 measurement, which is done in these two volumes over here. And using also the water volume, which we measure, Terry mentioned, by measuring the before and after weights of stripper. Our seawater DIC standards are prepared in lab, and you can see these IOS, that's the instant ocean standards. And there's a couple standards from the Seattle Aquarium, as well as the Puget Sound. And those are all measured somewhat regularly to track for any potential drifting or fractionation or leaks in the line, and it's just a great diagnostic tool for us. And as Terry mentioned, again, Andrew Dixon standards are used for DIC concentration calibration. And every once in a while, we'll run a blank about once a week to make sure that we're getting the full DIC possible out of each water standard, and that no fractionation occurring is the very first step of acidifying, or no DIC is being introduced in the line as we run each sample. So the Del 13 measurements are accomplished through the measurement of the dual inlet mass spec, which you see here. Here are those large bottles with the yellow tables are our working standards that Terry showed you. And then these bottles up top are our sample bottles that we freeze down the DIC in at the end of every run. And these are referenced to PDB. And then lastly, we have our RM 86562, which is used to scale lab CO2 standard. The PDB, as I just mentioned. Multiple lab DIC 13 standards are measured routinely to detect drift. We'll measure these standards against one another, as well as those working water samples and our working water standards and this reference material. And you can see our precision down here. And I think that is all I have. So, if anyone has any questions? Yeah.
Yes, we have time for one or two questions. If people would like to jump in.
So this is Wei-Jun. Do you, in extracting DIC, do you know like 99% or 99.9%? What is the precision, although that's not your main concern?
I believe our precision is 99.7. I'm not exactly sure on the number. I apologize.
Okay, thank you.
Maybe able to tell you that, but I don't want to put them on the spot.
Although this wasn't scheduled, I'm gonna take a 5-minute break for those of us who have been here for an hour and a half. So why don't we just come back in 5 minutes, and then Mashi, is that will speak? Is that okay? Sorry, but we'll get a fuller break later. So.
Hey, Mashi, would you like to try screen sharing? Oh, you're on mute.
Okay, share screen.
Yeah.
Sure.
Your sound is good.
Let's see. Do you already see the presentation?
I see it with the slides on the left. So if you make it full screen there, slideshow. Perfect.
Okay. Well,
And you can, your next.
I'll just send it now. So
Great. You can leave it up if you'd like, or just share again when we reconvene.
I'll just stop sharing and then.
Great. Thank you.
You're welcome.
So I am back. It's nice to finally meet you. Even if it is, what country are you in right now?
Are you talking to me, Anne?
Yes, I am, sorry.
Yeah, so right now I am in Spain, in the Canary Islands. So I was in Zurich until end of August, and then I start in January in London with Heather.
Oh,
And
so
now I got some months off to finish some papers, and well, I'm on holidays, but still doing
yeah.
some particular work.
Well, that sounds nice. The Canary Islands sound very nice.
It's like they say it's the equivalent of the European Hawaii. I never been to Hawaii, so I cannot tell. Probably it's nicer, but here it's very good already.
Well, during the pandemic, I've been learning South American Spanish, so maybe I should plan on going to the Canary Islands.
Yeah, it's a nice place.
Okay, 30 seconds.
Whoa.
Oof. Okay, I'm back. Yeah, and it's time for Mashi to speak. This is the first time I'm actually meeting him, although we've had many exchanges over email, and I was supposed to spend 2 months at the ETH lab just after the pandemic started, and partly to work with Mashi, but it didn't happen. And he's moved on since. Anyway, welcome and
so I'm gonna share the screen. Okay, do you see it?
Perfect.
All right, so thanks, Anne. I was a postdoc at ETH until August, as I said to Anne, and then I'm moving to London to work with Heather Graven at Imperial College. And today I'm gonna talk on behalf of the Laboratory of Ion Beam Physics about the work that we've been doing in the field of seawater and radiocarbon. Until present, we have used 2 different sample collection and preservation techniques. Most of our samples were collected into these glass bottles that allow for the collection of 100 milliliters of seawater. The bottles are previously cleaned using diluted HCl and deionized water. And then we transfer the sample from the Niskin bottles using silicone tubing. and the bottles are rinsed 3 times, and then we overfill the bottle with a sample by avoiding the formation of bubbles. Then we immediately close the bottle using a crimper, a rubber septa, and an aluminum cap. And then I use 2 syringes, one to remove, in case there is any air remaining in the sample, I remove the bubble with one of the syringes, and then I use another syringe to introduce the saturated mercury chloride solution. In a last step, because we only need 50 milliliters of seawater for radiocarbon determination, we systematically flush, helium flush half of the sample to another pre-cleaned helium flushed bottle. More recently, we have received samples that were collected by Joanna Lester from Heather Graben's group at Imperial College, and she followed the sample collection procedure described by the paper of Charlotte Bryant in 2013, which basically collects the seawater into a foil bag and preserves the seawater by keeping it at freezing temperatures. So a few months back, we got about 400 of these samples, which contain each of them about 400 milliliters, and we store them in our 600-liter freezer. And what we would do was twice a week or so, we would take out 35 bags and let them unfreeze overnight. And the day after, we would transfer them into the glass bottles as if we were sampling at the sea. And again, we would transfer half of the sample to a different bottle so that at the end we will have two subsamples. The first subsample is always acidified and heated overnight prior to analysis, while the second subsample is stored in the fridge, and we try to analyze it within a week or so. The method that we use, we started developing it back in 2017. It is one single line that couples both the extraction and graphitization steps. And it consists of an autosampler that is designed to extract the dissolved inorganic carbon from 7 samples in a row by helium flushing the seawater to extract the CO2. Then the CO2 passes through a water trap and goes into a furnace which has copper and silver in it, so that it can extract the trace compounds that can poison the iron that we use later as catalyst. Eventually, the CO2 goes into a molecular sieve trap, and from there, it's thermally released and transferred into each of one of these reactors by gas expansion. The system can also be fed by an elemental analyzer by direct combustion of the samples. And all this process from the CO2 extraction to graphitization is fully automated, and we can do it in less than 4 hours using only 50 milliliters of seawater and with a precision that is usually a bit better than 2 per mil. So that you see how much we can do in a very short time. What I'm showing now is the magazine that we use for the Lipmicadas, which contains 39 targets, and that we can prepare in just 2 days of work. And to ensure the high quality of the measurements, we try to follow always the same procedure or the same routine. In the first batch, we always prepare the NIST oxalic acid 2 and the phthalic anhydride blank using by direct combustion in the EA, and then which is directly fed into the H system. And in a second batch, we usually prepare a coral that is used as a reference. And this coral is dissolved in milky water that was previously acidified and helium flushed. Following a similar procedure, we also prepare IAE in C1 that is meant to represent the blank for the graphitization and extraction steps. And in later batches, we process the seawater samples. Up to present, we have already processed more than 1,200 seawater samples, excluding the replicates. And we are quite happy because we were doing this work somehow as a side project. And basically, since 2017, we started collecting samples in the Arctic, very few of them. That's when Nuria Casacuberta and Lucas Bakker, they started doing the first attempts to measure radiocarbon. And later we participated in different important transects along the Atlantic and increasing spatial resolution so that we could meet the recommendations made by OCB and McNichol. So in the following, what I'm going to show is the results of the blanks, the coral reference material, and the replicates. And for that, I will follow this same color coding of the cruises. And along the x-axis, I'm going to plot the data according to the time when they were processed. All right. So we have two types of different data sets. The field symbols, they represent the phthalic anhydride that is combusted in the EA and directly fed into H system, which has a measured value of 0.002 fraction modern. And then we have empty symbols, as you can see here, that show a lot greater scatter, which represent the procedural blank. As you can see, we had quite a lot of trouble for quite some time to get a procedural blank that is as good as the combustion blank. And it took us some time to realize that most of this variation and the high values were actually coming from the carbon contained in the molecule that we use to dissolve the IAAC1. Indeed, I know from talks with Lucas last week that they have managed to improve the procedural blank even to lower values so that it resembles the combustion blank by extending the flashing time of the molecule. And at this point, we have two types of blanks that we are sure of and that we can use for background correction. And to check the accuracy of the method, as I said, we use a coral sample, which has a nominal value. And so far, we have measured 80 samples of the coral value, and I have to say that they agree within 1 sigma value with the consensus value. Yet we are a little bit lower. And well, I'm not very much concerned because I think that this is partly lower because of the insufficient sampling, insufficient flashing of the molecule. But we are there and we are quite happy about this. The last thing I wanted to show is the reproducibility of the method, which we've been testing by measuring the second subsample regularly. Recently, we were doing one replicate every 7 samples. I don't know if this is overkilling it or not, but well, what I want to show you is we have data from the different cruises. They should all fall along the one-to-one line. They don't always do. But for example, if you look at the black data, they show quite a lot of scatter. These were the first ones that were measured in 2017 when we didn't have the copper-silver furnace. And if you look, for example, at other data sets, the yellow one or the blue one, when we already added the copper-silver furnace and we were a bit more careful with closing the bottles, we had a better agreement among the replicates. And the last data set that we've got is the green one. The green data, they correspond to the frozen samples that were collected in the foil bags. And I have to say that they have quite a good reproducibility that is comparable to the best that we got with when we were using the glass bottles. So to this point, I have to say thank you to all the people, especially Lucas, Nuria, and the technicians that were involved in developing this method and producing data from all these cruises. Also to Joanne Lester and Heather Graven for providing the samples from the 24 North cruise and the funding agencies. And I will be happy to answer any questions you may have.
Thank you. Do people have questions? There's time for one or two. Okay, I do have one. What do you think the copper silver furnace is scrubbing from the samples?
So I'm not totally sure. Probably Lucas can answer this better, but I think that it is about perhaps traces of sulfur and nitrogen oxides and halogens. That's what they said. I'm not entirely sure about this, but I know the reaction time improves a lot, and if you don't use this furnace, at least in our case, the reaction was most of the times not entirely completed. So it really improved a lot in our case, the reaction time.
Yeah, that's great, but seems a little odd.
I don't know.
For clean seawater samples, but whatever.
Yeah.
And frankly, I'm astonished at how well the foil bags are working, because I have never had success with them.
So regarding the foil bags, for us was the first time using them, and I have to say some of them had leaks and were broken. When after unfreezing overnight, we found that they were empty, up to 4 out of 100. So this means one sample per depth profile, for example. But this was the only disadvantage that I see. The rest was quite nice. You have more water that you can archive over long times. I think this is a great advantage. And then not using the poison, then it makes everything less toxic and more practical in the laboratory. So it's nice as well. I mean, we don't have much experience, but I think I would go again for these foil bags.
Okay, yeah, I actually know of people who have stuff that grow in those bags, but.
Oh, really?
Maybe
Okay.
they're different bags than these people were using. But anyway, it's fascinating. And I have to stop and turn it over to Wei-Jun Cai.
Can you hear me?
Yes, I can hear you and I can see the screen.
All right, okay. First, I want to thank the workshop organizers for giving me this opportunity to speak to you. And when I'm asked to prepare this talk, I prepare regular one, starting with the introduction. Now hearing previous talks, I realize that's totally unnecessary, but please bear with me. So the title of my talk is Analysis of Delta 13C DIC based on a whole water CO2 extraction device and cavity ring-down spectrometry detector. I'm Wei-Jun Cai from University of Delaware. So first start with scientific needs. Delta 13C DIC is a tool for determining the sources and sinks of dissolved inorganic carbon and for understanding carbon cycling in aquatic system. And also Delta 13C is a tracer for determining anthropogenic CO2 uptake rates by the ocean due to the atmospheric C13 SUSI effect, which is when you burn fossil fuel, you're adding very negative delta C13 CO2 into that. And when the ocean uptake that sea surface CO2, the delta C13 signals decreases, so that can combine with DIC will give you a more sensitive way to constrain anthropogenic CO2 uptake. That's being advocated by Paul Queer and others for 30, 40 years. But still today, most of us, the community, rely on the DIC method to constrain anthropogenic CO2. And I think the main reason is really because of the delta C13 data density is not as high as the DIC result. So I hope with this workshop and our effort in the future, we should be able to change the situation soon. I want to just quickly mention the reason to develop this method is because of limitation in the IRMS, the traditional method, which is very reliable, very accurate, but it's very time consuming. Although with current automation and previous talk, you can see actually they can do quite a bit of delta C13 analysis with IRMS. However, it cannot easily be deployed on board a ship or in a field lab on land. And another thing most of you probably don't talk is it also doesn't measure DIC concentration precisely, at least for the, like the commercial, the service center like UC Davis stable isotope facility. They don't really guarantee you DIC concentration. You guys probably do at 1% or 0.5% level. But for ocean carbonated chemists, our precision for DIC analysis is between 0.05% to 0.1%. So it has a great advantage to try to develop a method that simultaneously measures DIC and its isotope, and it can be deployed, portable and easily deployable for field work at sea or on land. So our goal is to develop a system that can do DIC better than plus minus 2 micromole per kilogram or 0.1% in seawater, and for delta C13 DIC better than plus minus 0.05 per mil. And right now, I think our system actually could do a little better than this, but because we are probably a new player, we're still learning how to develop accurate and easy to apply calibration methods. So that's a challenge to us. So this is our method, which the single part version was published in Marine Chemistry by Su et al. 2019, and the multi-channel is described in this Apollo SciTech web page. So essentially, our system has 3 parts. One is with a CO2-free compressed air, and mass flow controller delivers a constant rate of about 60 milliliter per minute, and it bubbles reactor a gas stripper and send it to a Piccolo analyzer. And the third part is just a digital pump, which delivers sample into and standard, right, into the reactor. So the procedure of doing this is first the digital pump draw acid into the syringe, and then it draw samples on top of the acid, because we use about 3% phosphoric acid, very diluted, but we add 7% of sodium chloride. So the density of this acid is twice of seawater. So you can see a very clear demarcation line of seawater above and the acid in the lower part. So when then this is pushed into the reactor, the acid actually cleans the syringe and the line. So you don't need to clean that line again. And then after stable baseline, you will push the sample and acid into the reactor and bubble it with, we use nitrogen, you can use helium, but I'm sorry, we don't use nitrogen, we use compressed air. That's because the Piccolo is sensitive to the composition of this air. So when we bubble and then it goes through a condenser to remove moisture, and since Piccolo has its own pumping rate at 28 to 30 milliliter per minute, so we actually went out about 50% of sample and doing the Piccolo measurement. This was from an earlier version. So the CO2 plus 12 plus 13 increases in a peak. So under the peak, it's the area under the peak is the total amount of CO2. And then you have the delta C13, which has a large noise when the CO2 12 concentration is low. and become stable when it's above like 100. But Picalo guarantees 400 ppm above that as a precision at 0.1 per mil, and when it's above 1,000, they guarantee 0.5 per mil. But because of the way we average this for a long time, actually, I think we achieve a better precision this way. So here's the way we calculate the DIC, which really is just the integration. So I've measured the CO2, subtract the baseline, and then multiply time, which is 1 second. And you just add all these bars together, integrate that. And then we take this bar as a weight. So you do the C13 average with this area weight. Now, although there's more noise when CO2 is still near this cutoff value, but because it's weighted approach, most of the data are dominated by high CO2 concentration part. And you could actually change the injection rate and the flow rate and sample volume to increase, make this peak more flat. And that's what we did in more recent system. We switched to a larger reactor and 10 cc, 10 milliliter syringe instead of 5. So this is the acid with the CO2 scrubber connect here. So we have two standards, standard 1, standard 2, and the samples. These are borosilicate glass bottle with this ground glass cap. When we start the measurement, we replace them with this cap with a breather and peak tubing. So here is a normal regular peak of C12 plus C13. And this is C13. You can see when concentration is low CO2, you have a lot noise of C13 is large because internally Picalo reference C13 to C12. But really, if you are focusing on measuring C13, this is all you need. So you don't need to wait until roughly we do one measurement at 520 to 40 seconds, and you can cut it off somewhere here if the DIC concentration is less important to you. But because our purpose is to get both precise DIC and beta C13, so we actually waited a completion of the integration, and we do 3 injections at least. So this is actually when you click that data instead plot, you will see this is actually a photo I took this morning. We did a standard from port C. So 1 volume, 4.5 milliliter. Normally we do 3, 4, 4.5, and 5 that create a calibration line for DIC concentration. And you can see the concentration, the 3, they're very close. And we set up a precision of 0.1%, but most time this is better than that. And if you look at the delta C13, although we set a 0.08 per mil, but when you look at the delta C13 reading here, they are much better than that. So since it's so stable from day after day, and we've been measuring this 1,200 samples we brought back from California current system. Actually, my postdoc, Amanda Timmerman and Chen Li went to the Dick Phillips West Coast acidification cruise from Canadian water all the way to Mexico water. Well, actually the US part, because of COVID, we can't get into further south. So they finished about 700 samples at sea and brought back 1,300-ish back home. And if you look, so this is the port D, E, F, G, so F all the way to K. So we can do 1 standard and 8 sample or 2 standard and 7 sample. And if you look at delta C13, they're really very close. Average 0.98 for this water, and you see 0.96, 97, 1.01. So much better than what is the standard we set up here. And you can do a lot of other adjustment to fit your needs. So here I want to show a cruise. We just came back last week. September 12 to October 22 at this Gulf of Mexico cruise. This went by Chen and Elliott. So we have these two standard bags, standard 1, standard 2, and this was just raw data of the Piccolo. So you can see for the 40 days, the overall deviation or drift is less than 0.05 per mil. We have a power failure once you started, and it's just very stable. Now remember, this is standard. So if we reference to the standard between them for the sample, I think the uncertainty will be smaller, less than this, okay? And so each point is really a repeat of 3 or 4 injection, and we get a stable performance in a ship-based working environment. And delta C13 is really not affected by ambient temperature, but we control in temperature for the DIC because we do the volume-based analysis. And we also seems we have very good long-term stability. And we also run CRM, and you can see this in the CRM. This year we are limited, so we only use 5 bottles CRM, but it's, overall it's still within better than 0.05 per mil. The entire we open 5, but when you do a few days later, it changes, of course. So both the bag of aluminum bag, it seems very stable, and the instrument could be very stable. We have 2 Piccolo units. 1 unit drifted.
Are you nearly done?
Yeah, I'm done. So I'm going to talk about the standardization procedure and the problem and challenges we face Wednesday. So I'm going to stop here.
Okay, thank you very much. We have time for 1 or 2 questions. I thought Rolfe was going to.
Rolfe?
I had a question for everybody in general, and it has to do with the precision that is reported. This is great, by the way. Thank you. One way of, well, if you look at this plot, you'll see a precision of 0.05, and if you do that, if you are referencing to 2 standards by quadrature, that you're about at 0.03. But what's the precision on replicate samples? The entire process going from the Niskin through the analysis. We're going to talk, I think, tomorrow quite a bit about how we actually report our output. So my question is, what's the precision on replicates at present? I know it's improving every cruise.
Yeah, so there are 2 things. One is from the same bottle, we do 3 injections. So they are actually better than 0.05 per mil. But we also do bottles from replicate bottle, like from the West California current system 1. We are still analyzing these data. So I only reported this from this 1 bag. Actually, this is from just 1 bag over 40 days. We didn't change a bag. But in the middle, when with a real sample, we do duplicates, and we will look into that. So yeah, that's definitely a very important issue to consider. Thank you.
Okay, we're going to take a half-an-hour break now. But before we go out, when we come back, we'll be splitting into breakout groups for discussions. And if you have questions that you think should be addressed in the discussion group, please add them to the chat, and I'll sort of organize them to give to each breakout group. I also wanted to ask anyone who's making measurements to make sure you fill out the poll that was sent out. It was targeted at people who are actually physically making measurements of C13 and C14 in seawater. I don't know, is there anything else general that I'm forgetting?